This computer. Here we go. We're going to record. Hi, kids. Welcome back. We're going to look at what's called Table E. Table E is on page 2 of the reference table. The front page, page 2. We're going to need that. Take it out. You're going to be able to touch it. Table E lists what are called polyatomic ions. Polyatomic means more than one atom. Two or more atoms bonded together that either lose or gain electrons and act as a single ion. They're groups that act like a single ion. They have a single charge. They act together. Atoms handcuffed together. I used to make this joke all the time. Imagine you and your best friend are going to go to the movies. Now that's hard because movies aren't open. But imagine you are going to show up to your friend's house, you ring the bell, and say, yo, friend, come on, we're going to the movies. And they say, my parents had to work. I have to watch my triplet little brothers. They're handcuffed to me. If you want to take me to the movies, we all got to go together. So instead of just you and your friend, it's you and the four of them, right? They're bonded together. They act as one unit. You can still bond to them, but they act as a single polyatomic ion. And they're all listed on Table E. There's actually more, but we only have to deal with about 20 of them, 22 of them. They're listed for you. Ready? Here we go. We know about monoatomic ions. Group 1, positive 1 ions. Group 2, positive 2 ions. Aluminum, positive 3 ion. We know about the transitional metals. Some of them make more than one kind of ion, more than one kind of cation. We have to use the Roman numerals. Some of them only make one kind of cation. We don't use the Roman numerals. And we even know noble gases don't make any ions. And the reason is because they're already perfect. Their outer orbitals are all filled, perfect. They don't need to bond. Bonding is stable. Bonding is get stable. It's okay to be an atom, but you're more stable when you're bonded together. Unless you're a noble gas, you're already stable. You're already perfect. You don't bond. We're now going to look at, instead of simple, instead of transitional, we're going to look at something called polyatomic ions. And Table E tells us what their names are and what their formulas are, and you don't have to memorize any of these unless you're in IB or AP Chem. Those kids, they get gray hair really quick. We just put our finger in a box. How easy is this class? Put your finger in the box and there's the answer. Open up your reference table. If you don't have reference table E open, you're never going to be able to do this. So hurry, go get it. Hit pause. I'll wait for you. I'll be right here when you get back. All right. Table E shows us what the polyatomic ions are. Poly means more than one, and here atomic means that they're stuck together. Polyatomic, stuck together. They act as a single ion. Now, most of them are negative. Only a couple of them are positive. Let's read the names out from the bottom to the top. We're going to read them backwards. Are you ready? I don't even know what the next slide is. Are we going to go through them? No, I'm going to have to just read them. We're going to start at the bottom. They have hard names, some of them. You won't have to say too many of them out loud, but you might. Ready? Thiosulfate, hydrogen sulfate, sulfate, and then sulfite. That's a very close one. Sulfate, sulfite. One letter difference. And there's only one slight difference in their formula. But they're not the same. You can't just be casual here. Sulfate, sulfite, totally different. Thiocyanate, phosphate. Here's one of my favorite ones, hydroxide. Now, Hydrox cookies are kind of like Oreos, and I like Oreos, except they get stuck in my teeth. My teeth are a little crooked, and the Oreos get stuck in them, but they taste good. Hydrox are like Oreos. They're the chocolate cookies with the white cream, but hydroxides, if you put them in your mouth, they dissolve your tongue and your teeth. It's really bad. It's kind of like the opposite of an acid. Hydroxides are bad, but hydrox sounds cool. Peroxide. Some of you have peroxide in a brown bottle under your bathroom sink. You can look. Brown bottle. It says hydrogen peroxide. It's not just peroxide. That's casual. But there is a peroxide polyatomic anion. Then you have nitrates and nitrites. They're both in your hot dogs, but they're not the same. One letter difference, one little oxygen difference, but they're not the same. This next one's fun to say, permanganate. That's a mouthful. Then you have two in a row that are also very similar, dichromate and chromate. Dichromate and chromate. Both have chromium and oxygen. Then on the left, bottom 4, you got 4 in a row that have chlorine and oxygen. You got perchlorate, chlorate, chlorite, and hypochlorite. 4 separate chlorine-oxygen combinations that are possible. Do you have to memorize them? No. Do you have to remember their names? No. Do you have to remember their formulas? No. How do you do it? Put your finger in the box. Then we have a really cool one called oxalate. Anything with an X is cool, right? Oxalate. Hydrogen carbonate and carbonate is similar, right? One's got a hydrogen, one doesn't. Carbonate, hydrogen carbonate, cyanide. Now, there's a bad one. You don't get any of that stuff in your body. I picked up a little jar once in chem lab in college. It said sodium cyanide, XXX for poison. You know what the side effects of ingesting sodium cyanide are? Instantaneous death. I picked up, I'm like, what is this even doing here? College is different. High school, we don't have that, of course, but some of this stuff could be bad. Then you have a really funky one. It's got two separate formulas. We're going to use the formula on the top, right? The top. I would even mark it right now. Put a little star next to it or something. See what I did? We're going to use the top one. For the bottom one, I'm going to put a little thing there. I'm going to write the word organic. Now, we'll learn about organic chem later in the year. Let me tell you something really quick. All chemistry is chemistry. Everything is made of atoms. Atoms bonded together to form different things. But for a while, scientists thought that there were special compounds made only by living things. And they called those compounds organic molecules. Organic for being like alive, and inorganic. Everything is inorganic, right? Everything we've learned so far. But organic is when the compounds were thought to be only be able to be made, not by labs, not by scientists, but only by living things. It's not really the truth, but there's different ways to write the formula, just like I have different names, right? You guys call me Mr. Arbuso because that's my name at school, and my wife calls me Honey Bunny. When I come home, sometimes she goes, Honey Bunny, you're home. She never calls me Mr. Arbuso. I'm exactly the same guy, but I have two different names. There's the same number of carbons, hydrogens, and oxygens. They both have a -1 charge, but one is the acetate ion written in what we call the normal or the inorganic chem style. That's the one we're going to use. Or the one underneath it, got a little fancy style, CH3COO. I like that too, but we're not going to use that now. Above that is a very, very common one, NH4 with the +1. All right, that's called ammonium. Above that is a weird one, Hg2 with a +2. That's called mercury Roman numeral 1, and that's because there's two mercuries and they each are a +1. And the very first one, yeah, I'm going to show you what I'm going to do. I won't even talk about it. I'm going to put a sad face right there because this is the stupidest thing in high school chemistry. Of all the things I'm going to teach you for the whole year, that, I think, is the stupidest thing in chemistry. Now, I'm not right. This is a personal quirk. This is an important thing in some ways. Stupid in high school chem. This is like the infield fly rule that you don't remember from when I told you about the baseball. It's one of these quirky things, but it's there, and it's coming back. I promise I'll talk about it in the spring. We're not going to talk about it now. It's there, but it's stupid. Okay. All of these have a special name, and we never change their name. You remember how we changed oxygen to oxide and bromine to bromide and all that stuff? Not here. If we're using the polyatomic ions, the last names never change. So if it comes out as permanganate, we're not going to make it permanganide. No changing the names. No. Some of them actually end in IDE, right? Peroxide, hydroxide, a couple of them. We're not changing these names. The rule is, why? Just because I told you, because there's too many things to talk about. Just, you're going to have to let it go, right? You know what you should do? Right now, somewhere over here. See over here in this space? Right. Never change these names or else. Or else. Now, let's start looking at this very first one. This is called ammonium. Ammonium is an atom of nitrogen that's bonded to 4 hydrogen atoms. There's 5 atoms total, 1 N, 4 H's. And out of that combination, it's lost a single electron. So this whole polyatomic, this whole chunk of 5 atoms bonded together, loses a single electron. It has a +1 charge, just like a sodium atom has a +1 charge. But in this case, lithium also, +1 cation. This is a +1 cation, except it's a polyatomic. It's a group of 5 atoms acting as a single +1 ion. They will handcuff together, those 5 atoms. They come as a chunk. They have their own name, ammonium. Now, let's see how this works. If we had Na cation, +1 with chlorine, it's going to bond in a 1-to-1 ratio, and it's going to be called sodium chloride. There's a transfer of 1 electron. The sodium atom loses an electron, transfers it over to the nonmetal. They end up wildly attracted together, +1 or -1, and they make a neutral ionic compound. Same thing could happen with ammonium and chlorine. Ammonium can transfer 1 electron over to chlorine. Chlorine becomes a -1, the ammonium is a +1, and they go together in a 1-to-1 ratio. Ammonium chloride, wildly attracted together. Very strong positive-negative charge bonded together. It's an ionic compound, except instead of a monoatomic cation, we have a polyatomic cation, and we just give it a name, ammonium chloride. It's really easy to name. Watch what happens. These are the rules to name. The cations still go first all the time. The anions still go second all the time. Nothing changed so far, but number 2, never change the name of the polyatomic ions. Whatever name they have, that's the naming rule. This is so easy. So there, I just told you in purple. Never ever change the name of these ions, or else. Or else. So they're going to be easy, right? Couple extra letters and numbers, going to be easy. Don't you worry about it. I got you hooked up here. So we're going to have to write the ions. I already wrote them for you. Look, down the left column, first column, second column, I gave you the cations and the anions and their charges. You got a great teacher. He gives you everything you need. Now, how are we going to do this? This is a little tricky, right? I'm not kidding. It's a little tricky. Look at all these letters and numbers. Let me start drawing here. Let me get my little arrow business going, and I think I'm going to write in a red color this time so you see it. This sodium has a +1 charge, so we have to do the crisscross business. And this ion here is called acetate ion, has to go across. So we're going to crisscross the ones, the +1, -1, and guess what? We don't write ones in the formula. So what's going to happen then? What's going to happen? We're going to get this, NaC2H3O2. Now the C2H3O2 is called the polyatomic anion, and its name happens to be acetate. It's the one right underneath ammonium. The fourth one down on the left column, table E. No numbers, right? The sodium gets a 1 and the acetate gets a 1. Now, the C2H3O2, there's 2 carbons, 3 hydrogens, and 2 oxygens. That is 7 atoms bonded together in a group that has a -1 charge. So the way you see this in your head is we need 1 sodium and 1 acetate. If you're typing or if you're writing, there's no space between sodium and carbon, or sodium and the acetate ion, right? Na, we don't write the 1, and then it's C2H3O2, we don't write the 1 again. And the stock name, or the name of this, what's the rule? Say the name of the metal, say the name of the polyatomic ion without changing the name, sodium acetate. Now, you know what? There's a lot more letters and numbers, but it's not a moving thing, right? You put your finger in a box, C2H3O2, there it is. Just write it again. Next one's a little easier, right? We started hard, it gets really easy. This next one, let me get some more ink going. I'm going to get the color change. We're going to, oh, here's a nice pretty color, and we're going to use this one. The +1 for K+1, that's going to go over here. That's potassium cation. What the heck is CN? Put your finger in a box. Where is that one? Eeny, meeny, miny, mo. It's over here. See it? CN, and what do we call that? Look at the name, it's right there. You don't have to think about it. It's certainly not carbon nitrogen. The Cn -1 ion, that goes over here. We're going to crisscross. Say it in your head. We're going to need 1 K and one of those Cn ions. So how do you write it? No spaces? Just, like you were typing. Here we go. KCN. And it's called potassium. Don't change the name of the polyatomic ion now. Potassium cyanide. It's not hard. This is not hard. Uh-oh, the next one's a little hard. I tease. Not hard. +2, -2. What did John Dalton say? Simple whole number ratios. So when you crisscross, look, I'm going to use blue again. No, I don't even have the ink. Since I got to turn this thing on, I'm going to use a different color again this time. Oh, here's a good color. You never saw this color before. This 2 goes over here. This 2 goes over here. So in your head, you might say, wait, I need 2 magnesiums and I need 2 of those CO3s. The heck is CO3? You got to put your finger in the box. Look, it's right here. CO3, can you see it? Carbonate. Say it, I need 2 magnesiums and 2 carbonates. What is 2 to 2? 1 to 1. So you don't need 2, you need 1 to 1. You got to remember, John Dalton said simple whole number ratios. 1 Mg, 1 carbonate, no spaces, write it tight, MgCO3. That means 1 Mg. And CO3 is a unit. There's 1 carbon and 3 oxygens. It's called magnesium carbonate. Now, the polyatomics, honestly, mostly are pretty easy. I'm going to try to erase my drawings now. Annotate. I'm going to clear my drawings. They're easy, except if there's multiple polyatomics. A little extra rule. No big deal. Say it out loud, though. For the first one, I got 1 sodium. I need 1 acetate. I got 1 acetate. I need 1 sodium. So 1 to 1. No problem. Same thing for potassium cyanide. And the same thing for magnesium carbonate. Now, when there are multiple polyatomics, we got to deal with that. For instance, we're going to do this one of my favorites, hydroxide. Remember I told you about the cookies? A magnesium cation makes a positive 2 ion. And the hydroxide, here it is, see it? Hydroxide, negative 1. So if there's a positive 2 and a negative 1, it's not a 1-to-1 ratio. So you have to say this in your head. The electron transfer is going to be perfect. We're going to crisscross. I'm going to get my arrows again. Let me see if I can get my ink back out here. It hides on me, and then it's hard to get back. But we need this here, and then we need this here. Now, think. Don't write. Think. I'm going to need 1 magnesium, but I'm going to need 2 hydroxides. How am I going to write 2 hydroxides? There's a rule. There's a rule. So, next, let me get rid of this. I'm going to jump ahead. When we crisscross, oh, look, I got it up on the top. How cool is that? And I'm going to erase my other drawings. Crisscross. We're going to have to use parentheses now. If we use parentheses, it will be able to be written really, really easy. Say it. 1 magnesium, and we need 2 hydroxides to make something called magnesium hydroxide. All right? Where is it? Oh, I didn't even do it. I'm going to have to do it. I lost a slide. So let me hit this and put it in right here. This is the way to do it. I'm going to change the ink color too so you can see it. We'll do it in blue. And I guess I'm going to back that up. And it's going to be Mg. Oh, I thought I was going to do it in blue. Mg, I only need 1. And then I put parentheses, OH, and then a little 2. And it's got to be a font. See how I do that? Font subscript. And I'll hit save. It takes a long time to save because this is a really, really big slideshow with so many slides. So it takes a while. It even says it's not responding, but it always responds. All right? So we got magnesium sulfide. Magnesium hydroxide. Can you see I made another dumb mistake? MgOH2. You could say this MgOO. You know what a lot of kids do? A lot of kids might write MgOH little 2. But what does that mean? That means there's only 1 oxygen and 2 hydrogens. That's not right. We need 2 OHs. The OH anion, hydroxide, we need 2 hydroxides. So we put the multiple polyatomic ion in a parenthesis and multiply it. So it's MgOH2. Honestly, a little tricky. We're going to do some more. But you got to be careful because you only need parentheses when you need them. Soon you're going to put parentheses everywhere, even in NaCl. You're going to learn to like parentheses. Put them everywhere. You might write this, magnesium Roman numeral 2 oxide. Remember that? We don't need Roman numeral 2s for that. We're not going to need parentheses. All of a sudden, they're going to be everywhere. Go slow. Here we go. We're going to do these really slow. Let's look at the example. Na plus 1, Cl negative 1. The formula is NaCl. It's called sodium chloride, crisscross. Except now we got polyatomics. Here we have the Li plus 1 ion, which is called the lithium positive 1 cation, and CrO4, which is a negative 2 ion. That's called chromate. Chromate's on table E. Look, it's right here on the top. Got my finger in the box. I don't happen to memorize this one. So if it's Li plus 1 and chromate is at -2 and you crisscross it, say it in your head first. We're going to need 2 lithiums and only 1 chromate. So let's crisscross and see what we get. Oh, I gave you the rest of these. I don't know what's going on, why they came up that way. But we'll get to them. Let's see what we got. Li2 and the chromate, we only need 1 chromate. The chromate is a -2 ion. We need 2 positive ones and a -2. It sums to neutral. And how do we say the name of this? Say the name of the metal, lithium. Say the name of the polyatomic ion without changing the name, lithium chromate. Now, honestly, that's a big funky formula, Li2CrO4. That's how you say it, Li2CrO4. There's 2 lithiums, 1 chromium, and 4 oxygens. But the CrO4 acts as a group. Now, you can't know this. You're going to have to get used to this, right? We're going to use these polyatomics a lot. You're going to have to say 2 metals can never come together. If there's a metal like lithium and another metal follows, it must be connected to a polyatomic. I got to look on table E. All right, this next one in black, number 73B. You got the aluminum positive 3 cation, and then you have ClO. What the heck is ClO? You don't know. Look at this. ClO. See it? Called hypochlorite. Now, when we crisscross, think first. Say it to yourself. I'm going to need 1 aluminum, but I'm going to need 3 hypochlorites. So when I crisscross this, I have to put the ClO in parentheses and triple it. There's only 1 aluminum, and this says whatever's in the parentheses is now tripled. And I have to crisscross. I got to have 3 ClO groups, 3 of these things that are called hypochlorites. And the name, of course, is just say the name of the metal and say the name of the polyatomic ion. It's called aluminum hypochlorite. I think I said sodium in there. Aluminum hypochlorite. This next one in blue, 73C. Magnesium is a positive 2 ion. There's no choice on that. It's in group 2. SCN. Uh-oh. Table E. SCN. That's 3 different atoms. See it in there? 3 different atoms. Thiocyanate. How cool is that to say? Thiocyanate makes you sound like really smart. Crisscross. You're going to need 1 magnesium and you're going to need 2 thiocyanates. So what is it going to turn into be? Look at that. Now, some of you might say, well, why don't we write MgS2C2N2, right? I mean, that's kind of the same thing, but it's not. The SCN is a unit. And the way it's written here in blue, SCN in parentheses with a little 2 means there's 1 magnesium bonded to 1 SCN group and the magnesium is bonded to a different SCN group. It's not S2C2N2. John Dalton said these are the formulas. We use them in simple whole number ratios. This is a 1 magnesium to 2 of the thiocyanates. And here we go. The other answers came up so quick. The calcium's a +2. The permanganate is a -1. And when we crisscross, we need 1 calcium and 2 permanganates. And it's called calcium permanganate. See what happened? I put them out of order. I took it out of the wrong one. I gave you the answer and I went backwards. I don't know how that happened. There it is again. I guess I got an extra slide in there. All right. This time for 74, which I think is the last, this is the last one. We'll be done. This is a short class. We're going to go backwards. I'm giving you the names. You need to get the formulas. But truthfully, it's going to be way easier if you figure out the ions first, the cation and the anions. Then you'll get the formula. So the name, beryllium phosphate. What do you got to do? Well, you got to figure out what are the ions. Beryllium is on the periodic table. And phosphate is PO4 with a -3. Now, what does that mean? That means 1 phosphorus and 4 oxygens, 5 atoms altogether, combine, and all together they have to give away 3 electrons to gain 3 electrons to be a -3 ion. Berylliums, though, lose 2 electrons, and 2 and 3, they don't match up. We got to do the crisscross business. This is a big crisscross, right? So we're going to need 3 berylliums, and we're going to need 2 phosphates. So what's this formula going to look like? It's a big formula, for real. Be3, PO4 twice, right? You can say this a lot of ways. Be3, PO4 2 times. beryllium phosphate. Say the name of the metal, say the name of the polyatomic anion, and take a deep breath, right? Because this is hard. You're like, oh gosh, my head is exploding. There's too many of these. There's not too many. It's your first day. It's the first time you ever even heard of these things, right? It's going to take practice, right? The first time you picked up a bowling ball, did you throw a strike? Maybe you did. Good for you, or maybe bad for you. You thought it was easy. It takes practice. You're going to have to practice these. I'll give you plenty of practice. Don't you worry. 74B, sodium hydrogen carbonate. Sodium is easy, Na+1, and you're going to have to say, what the heck is hydrogen carbonate? Look, it's right here, and there's the formula, HCO3 -1. So you write the ion charges down, and now how do you come up with the formula? Well, you got to do the crisscross business. Look, +1, -1, they crisscross 1 to 1. They don't write numbers. So just kind of squash them together, and the answer pops out. Look at that, NaHCO3. You know what this stuff is? You used it. Well, you saw it in lab. This is baking soda. Baking soda, sodium hydrogen carbonate. It's in a 1-to-1 ratio. The sodium is a monoatomic cation combined to a polyatomic anion. 74C, we got ammonium, that's a cation, and we got nitrate, which is a polyatomic anion. They're both polyatomic. They're both on table E. So let's see. I think these come up all together. There we go. The NH4 is a +1, and the NO3 for nitrate, make sure you don't pick nitrite. That's something different. Nitrate has a -1. Crisscross, 1-to-1 ratio. So we just write it the way it is, NH4, NO3. Now these numbers, we would never ever change them. Ammonium has 5 atoms, nitrogen and 4 hydrogens, 5 together. And the nitrate is 4 atoms, the nitrogen and 3 oxygens. So that's 4 altogether. We keep those numbers. The whole thing, we got 1 ammonium and 1 nitrate. No spaces, just squish them together. Now the last one's a big one. Ammonium dichromate. Ammonium is still going to be NH4. Dichromate is the biggest polyatomic ion we have. It's got 9 atoms in it. Holy smokes, right? And what do we got? Cr2O7. Now this is dichromate. It's not chromate. Chromate is chromium and oxygen, but it's a smaller one. This is the big one. This is the big kahuna. Now look, we got a +1 and a -2. When we crisscross, you got to say to yourself, hey, I got to have 2 ammoniums, but I only need 1 dichromate. That's because the dichromate's a -2 ion and the ammonium's a +1. You need 2 +1s and a -2. This time, we got to move the parentheses to the front, to the cation, and the formula comes out like this. NH4 double, 2 ammoniums, and then 1 dichromate. Now, honestly, look at that crazy formula. NH4 parentheses 2 Cr2O7. That's a big formula, but it's made up of parts. First of all, ammonium is on table E and dichromate's on table E. But even if you look deeper, you have nitrogens and hydrogens and chromiums and oxygens. There's only 4 kinds of atoms in this. There's going to be 2 nitrogens and 8 hydrogens altogether because it's NH4 twice, NH4, NH4. So there's 2 nitrogens, 8 hydrogens, 2 chromiums, and 7. So we're looking at 19 atoms bonded together to make this one thing called ammonium dichromate. All right, I lied. This is the last slide. This is the last 2. I promise we're done. Again. And it says, ooh, really hard ones. 74E, bismuth. Bismuth. Oh, Roman numeral business. We got Roman numeral polyatomic with Roman numerals with polyatomics. That's fine too. Write the ion charges. So for this one, bismuth, Roman numeral 5, is a +5 ion. And this thiosulfate thing, thiosulfate is right over here. It's the last one. And it's S2O3. 2 sulfurs, 3 oxygens, gains 2 electrons. Now, bismuth here has to give away 5 electrons, and the thiosulfate only gains 2 electrons. So when we crisscross, whoa, the numbers are big now. We're going to need to do 2 bismuths and 5 thiosulfates. 2 bismuths crisscross. So I'm going to even get the arrows out. Let me get the arrows out here because this one is a little tricky. We're going to need 5 of these and 2 of those. Make sure you can see this, all right? We're going to need 2 bismuths and 5 thiosulfates. And how are we going to get that? it's going to look like this. Bi2, and then in parentheses, the thiosulfate, S2O3, 5 times. Bismuth, Roman numeral 5, thiosulfate. What about the name here? Say the name of the metal cation. If it's a polyatomic, might have a middle name with a Roman numeral. If it was calcium thiosulfate, you would need a Roman numeral because calcium doesn't have a Roman numeral. But if it is a metal in the periodic table that has more than one possible cation, got to have a Roman numeral. And this last one, cobalt, which one is cobalt? You got to look. Cobalt's right next to iron. It's number 27. Cobalt here makes a positive 3 ion, and chlorate is this one right here. See it? ClO3. That's a polyatomic. So what are we going to do? Cobalt with a +3 cation. That needs to be +3. I'll fix that in a minute. It's too low. I have to make it a superscript. And then ClO3. That's 1 chlorine and 3 oxygens combined, 4 of them atoms together with a -1 charge. And when we crisscross it, let me get the arrows going again. Where's my arrow drawing business? Arrows. And I'm going to go back to this color. Where is the arrow? We're going to need 1 cobalt, and we're going to need 3 chlorates. Crisscross. 1 cobalt, 3 chlorates, and I guess I got to get rid of this, and look at that. CO1, we don't write the 1, and then ClO3 is tripled because we need 3 of them. Cobalt, Roman numeral 3, chlorate, the name. Say the name of the cation. In this case, the name of the cation has a middle name, Roman numeral, and say the name of the polyatomic ion without changing it. And that's it. We be DONE done. Listen, none of this is hard, but there's a lot. There's a lot. There's 22 of these polyatomics. There's a whole bunch of Roman numerals. There's group 1 and group 2 metals, a simple and aluminum that's simple. There's a whole bunch of anions on the periodic table. Those are monoatomic. You got the polyatomic, the monoatomic. You got the group 1, group 2, and aluminum. And you got all the transitional ones. Then you can combine them in different combinations. They got funny names. Some of them you have to change. Some of them you don't have to change. But you're writing this all down. Don't change table E names, and change the group 17, 16, and 15 anion names to IDE. Honestly, it's not that much. But at the same time, I've taught you how to write the names of probably 9,000 compounds already in just a few slideshows. So it's a lot. It's going to take practice. Don't think you have this yet. It's okay, but remember, you're going to start putting parentheses everywhere. You don't want to do that. You only need them when there's more than 1 polyatomic ion, not when there's 1 polyatomic ion. You're going to want to start using Roman numerals for everything. You'd only use them when you need to, when there's more than 1 possible cation, or you're going to forget them, right? There's no such thing as bismuth thiosulfate. There's 2 different kinds of bismuth cation. You got to tell me which one it is. And we haven't even gotten to the molecular compounds yet, things like carbon dioxide that use prefixes that have no metals, right? They're coming soon. That's the next slideshow. It's really cool. You're learning a lot of chemistry. This section, oh my goodness. You go from what? You go from sodium chloride, carbon dioxide, maybe carbon monoxide. What else you know? Maybe magnesium oxide you picked up. You got the formulas for 9. You can write the formulas in the names for 9,000 compounds, right? Let me take a bow. I'm working hard. All right. Let me end this slideshow because I've had enough of this, and so have you. Peace, love, and chemistry.